Let's say you want to deploy the following pod to Kubernetes. You could use kubectl and apply the YAML file. Now, when you type kubectl apply, a few things happen. First of all, kubectl will read your local Kubernetes config, and then it will reach out to the Kubernetes API server and discover APIs. This simply means it will check the available APIs and how they can be used. Then kubectl will perform client-side validation to check for any obvious errors and typos in your YAML file. And finally, it will convert your pod to a JSON object and send a request with that payload to the kube API server. When the kube API server receives a request, it doesn't store it immediately in the etcd database. First, it has to verify that your request is legitimate. That is to say, it has to authenticate your request. Once the request is authenticated, it needs to check if you have permission to create those resources in the request. Just because you have access to the cluster, it doesn't mean you can create or read all the resources. The authorization is usually done with role-based access control, RBAC. It allows you to assign granular permissions and restrict what a user or an app can do. RBAC roles are frequently aligned with the physical structure of your teams, apps, and departments. You could create roles such as developer, manager, and maybe admin. Now, in more practical terms, the API server follows these steps. When it receives the request, it authenticates the user. If the validation fails, it will reject the request and return 401 unauthorized error. Otherwise, it moves to the next step. When the user is authenticated, it checks if they have access to the resource. If they don't, it will reject the request and return 403 forbidden error. Otherwise, it will continue executing the request. In this video, we'll focus on the authorization part. The RBAC model is designed to grant access to resources based on the roles of individual users within the organization. To better understand how it works, let's take a step back and pretend that you had to design an authorization system from scratch. So how could you ensure that a user has right access to a particular resource? One of the simplest solutions could be to create a list with 3 columns like this. You could have user, permission, and resource columns. In this example, John has read and write access to app 1, but has no access to app 2. Robert and Jennifer have only read access to app 2 and have no access to app 1. This approach works fine with a small number of users and resources, but can be hard to scale up. Let's say that Robert and Jennifer are in the same team, and they are granted read access to app 1. In that case, you would need to add the following entries to your table. That's great, but it's not obvious that Robert and Jennifer have the same access because they are the part of the same team. In a typical authorization system, you have users who access resources. One way you can assign permissions is directly to a user and define what resources they can consume. These permissions map directly to the resource. Notice how they are user-specific. If you decide to have a second user with the same permissions, you will have to duplicate the entry. Now, to solve the previous problem, you could add a team column to your table, but a better way is to break down the relationships. First, you could define a generic container for permissions, a role. Then, instead of assigning permissions directly to users, you could assign those permissions to the roles. And finally, you could link roles to users. Let's see how this is different. Instead of having a single table, now you have 2. In the first table, permissions are mapped to roles. In the second table, roles are linked to identities. Let's say you want Robert to be admin for app 1. You can add the role to the user like this. At this point, you should understand how decoupling users from permissions with roles can improve security administration in large companies with many users and permissions. When using RBAC, you have users, resources, and roles. The permissions are not assigned directly to a user. Instead, they included in the role. The users linked to the role with binding. Since roles are generic, when a new user needs access to the same resources, you can use existing role and link it with a new binding. Kubernetes also uses RBAC model to protect resources inside the cluster. It utilizes the same three concepts explained earlier: identities, roles, and bindings, but calls them by slightly different names. Alright, let's go over example that needs to grant access to pods, services, and other resources. First, we have a service account, which is identity of who is accessing the resource. Next, we have a role that includes permissions to access the resources. And finally, we have a role binding that links the identity, which is a service account, to the permissions defined in the role. After you submit these definitions to the cluster, the application using that service account will be allowed to issue requests to the following endpoints. If you have never created RBAC objects yourself, but only relied on the provided roles with the applications, it can be a bit confusing. You may be wondering what resources exactly you're granting access to, what a service account is, and why the role contains a list of Kubernetes objects. To better understand how this works, let's set aside the Kubernetes RBAC model and try to rebuild it from scratch. We'll focus on three elements: identifying and assigning identities, granting permissions, and finally linking identities to permissions. Let's say someone on your team wants to log in to Kubernetes dashboard. In this case, you should have entity for an account of a user, with each having unique name or ID, such as email address. Now, how should you store the user in the cluster, considering Kubernetes doesn't have objects that represent regular user accounts? So users cannot simply be added through API call. Instead, any actor representing a valid certificate signed by the cluster's certificate authority is considered authenticated. In this case, Kubernetes assigns the username from the common name field in the subject of the certificate like this. And a temporary user object is created and passed to the authorization RBAC module. This is the code snippet from the Kubernetes, which is a Golang struct that maps all the details collected from the authentication module. Just keep in mind that the user is used for humans or any external applications to the cluster. If you need to create identity that will be used inside Kubernetes, you should use a service account. It is very similar to the regular user, except that it is managed by Kubernetes itself. A service account is usually assigned to pods to grant permissions. For example, you may have Prometheus deployed inside the cluster that needs to discover its targets, or perhaps Nginx ingress controller that must have permissions to list all the backend endpoints for a service. For those apps, you can define a service account. Since service accounts are managed within the cluster, you can create them as any other Kubernetes resources via YAML file. You can also define a group of users or service accounts. This is convenient if you want to reference all service accounts in a specific namespace. At this point, you have a mechanism to identify who has access to a resource. It could be a human, application, or a group of them. But what resources are they accessing in the cluster? In Kubernetes, we're interested in controlling access to resources such as pods, services, endpoints, and so on. These resources are usually stored in the database, etcd, and accessed via built-in APIs like this. Now, the best way to limit access to these resources is to control how those API endpoints are requested. For that, you would need two things. First, the API endpoint of the resource itself, then the type of permission granted to access the resource. For example, read-only, read-write, etc. So for the permissions, you will use a verb such as get, list, create, patch, delete, etc. Now, let's say you want to get, list, and watch pods, logs, and services in the Kubernetes. You could combine those resources and permissions in a list like this. You could simplify the definition and make it more concise if you notice a few things. First, the base URL, API v1 namespaces, is common to all. Well, maybe we could drop it. Then you could assume that all resources are in the current namespace and drop the namespace path as well. This looks better. The list is more human-friendly, and you can immediately identify what's going on. But there is more. Besides APIs for built-in objects such as pods, endpoints, and services, Kubernetes also supports API extensions. For example, when we deploy the Prometheus operator to our cluster, it also creates custom resources. These objects are also stored in the cluster, and you can query them using kubectl. Additionally, custom resources can be accessed via Kubernetes API. If you want to map those into a YAML file, you could write the following by dropping the base URL and namespace. Well, it's nice and short, but how does Kubernetes know that those resources are custom? So, how can it differentiate between built-in APIs and custom APIs? Unfortunately, dropping the base URL from the API endpoint wasn't such a good idea. You could restore it with a slight change. You can define it at the top and use it later to expand the URL for the resource. Now, what about resources such as pods that don't have a namespace API? For that, Kubernetes provides empty API group, which refers to the built-in objects. So the previous definition should be expanded to the following. You have two cases when Kubernetes reads the API group from the YAML file. If it's empty, Kubernetes expands it to API v1 and the resource. Otherwise, it uses the following pattern. So all your built-in resources will be expanded to the following endpoints, and custom APIs will use a slightly different pattern. Now that you know how to map resources and permissions, it's finally time to combine them together with multiple resources. In Kubernetes, a collection of resources and verbs is called a role, and you can group roles into a list. Each role contains the API groups, resources, and verbs that you just learned. A collection of roles has a specific name in Kubernetes, and it is called a role. Alright, so far we modeled identities with users, service accounts and groups, as well as permissions to resources with roles. The only missing part is now how to link them together. Now, to grant permissions defined in the role to a user, service account, or a group, we use RoleBinding. Let's have a look at this example. This definition has two important fields. First is role ref that references the viewer role. Next is subjects. It links to the My App service account. As soon as you submit this role binding to the cluster, the application or user using the service account will have access to the resources listed in the role. But if you remove the binding, the app or user will lose access to those resources, while the role itself will stay ready to be used by other bindings. Take a look at the subjects field again. It is a list that contains kind, name, and namespace. The kind property is used to differentiate between users, service accounts, and groups. But what about namespace? In general, it's often helpful to break the Kubernetes cluster up into namespaces and limit access to namespaced resources to specific accounts. This is helpful when you share the same Kubernetes cluster between multiple teams. In most cases, roles and role bindings are created in a specific namespace and grant access only within that particular namespace. However, there are some edge cases when you can mix cluster roles with role bindings, granting access to a different namespace. You'll see this later. Before we move to the next topic, let's have a look at a few examples of how the subjects field is used. In this case, when the namespace field is not specified, this targets all service accounts in all namespaces. You can also have multiple groups, users, or service accounts as subjects like this. Let's go over a quick exercise. Let's say you have a staging and production namespaces in your Kubernetes cluster, and you want to grant the QA team only read access to the staging namespace. For example, they should be allowed to get list pods and services as well as to get logs from those pods. By the way, all the source code is available in my GitHub repo. Now, because we use Minikube to simplify this exercise, I'll create a service account instead of a user, but the logic is exactly the same. First of all, we need to create a service account for the QA team, which will be located in the staging namespace. Then let's create a role which would allow QA to get pods, services, and retrieve logs from those pods. And finally, we need to bind the QA service account to the QA role. And I also have a couple of pods, one located in the staging namespace and the other one in the production namespace. One way to pretend to be a QA team member is to impersonate that service account. So we can use the following command to check if QA can get pods in the staging namespace. Yes, we can. Now, what about production namespace? Nope, we don't have permissions to access prod. You can also try to get logs from the pod in the staging namespace. Yep, we can access it. When we discussed resources, you learned that endpoints have the following structure. But what about resources that don't have a namespace, such as persistent volumes and nodes? Namespace resources can only be created within a namespace, and the name of that namespace is included in the HTTP path. If the resource is global, like in the case of a node, the namespace name is not present in the HTTP path. Now, can you add those to a role? Well, yes, you can. After all, we didn't discuss any namespace limitation when we were talking about roles and role bindings. Here is an example. If you try to submit the definition and link it to a service account, you might realize it doesn't actually work. Persistent volumes and nodes are cluster scoped resources. However, roles can only grant access to resources scoped to a namespace. If you would like to use a role that applies to the entire cluster, you can use a ClusterRole and the corresponding ClusterRoleBinding. To make our previous example work, you only need to change role to ClusterRole. Everything else stays the same. You can also use ClusterRole to grant permissions to all resources, for example, to all pods in the cluster, instead of just in one specific namespace, such as staging. This functionality isn't restricted to cluster-scoped resources, like persistent volumes. Kubernetes actually ships with a few roles and cluster roles by default. Let's take a look at them. You can use grep and use system as a filter to get roles that are directly managed by the control plane. Also, all of the default cluster roles and cluster role bindings are labeled with the following label. Let's also list the cluster roles. You can also inspect the details of each role and cluster role with the following command. At this point, you know the basic building blocks of Kubernetes RBAC. How to create identities with users, service accounts, and groups. How to assign permissions to resources in namespace with a role. How to assign permissions to cluster resources with a cluster role. And how to link roles and cluster roles to subjects. There is only one missing topic left to explore, a few unusual edge cases of RBAC. At the high level, roles and role bindings are placed inside and grant access to a specific namespace, while cluster roles and cluster role bindings do not belong to a namespace and grant access across to the entire cluster. However, it is possible to mix these two types of resources. For example, what happens when a role binding links an account to a cluster role? Let's explore this next with some hands-on practice. Let's start by creating a local cluster with Minikube. To start, let's create 4 namespaces. And finally, create a service account in the dev namespace. You can also submit the service account using apply command. At this point, your cluster should look like this. Let's start with creating a role and role binding to grant the service account access to the dev namespace. We have the role, which is placed inside the dev namespace, as well as role binding for that service account. After you apply this, your cluster should look like this. All resources, service account, role, and role binding are in the dev namespace. The role grants access to all resources, and the role binding links the service account and the role. Well, how do you test that the service account has access to the resource? You can combine 2 features of kubectl. You can use user impersonation and verify API access with the following commands. To issue a request as myapp service account and check if you can list pods in the namespace, you can issue the following command. Let's break it down. auth-cana is necessary to query authorization model, RBAC. Get pods is the verb and resource. -n-dev is the namespace where you want to issue the command. And --s system service account dev myapp is used to impersonate the myapp service account from the dev namespace. The entire string can be broken down to the following pattern. With this role service account role bindings combination, you can access all resources in the dev namespace. Alright, let's move on to a more complex example. Let's create a new role and role binding in the staging namespace. Notice how the role binding links the role from the staging namespace and the service account from the dev namespace. Okay, let's go ahead and apply. At this point, your cluster should look like this. Now, let's test if the service account located in the dev namespace has access to the resources in the staging namespace. This works. We just granted access to the resources outside the namespace where the service account was created. It's worth noting that the role ref property in the role binding doesn't have a namespace field. The implication is that a role binding can only reference a role in the same namespace. Now, let's take a look at cluster roles. As you remember, they do not belong to any namespace. This means that cluster role doesn't scope permissions to a single namespace. However, when a cluster role is linked to a service account via role binding, the cluster role permissions only apply to the namespace in which the role binding was created. Let's look at the following example. Create a role binding in the QA namespace and link the service account to the cluster role cluster admin. The cluster admin is one of those built-in cluster roles in Kubernetes created when you provision a cluster. Alright, let's submit this. Now your cluster looks like this. Let's test if the service account located in the dev namespace has access to the resources in the QA namespace. However, it doesn't have access to other namespaces. In this scenario, when you use role bindings to link service account to a cluster role, the cluster role behaves as if it were a regular role. It grants permissions only to the current namespace where the role binding is located. In this last scenario, we'll create a cluster role binding to link the cluster role to the service account. Note that we don't have a role ref field here. This implies that a cluster role binding cannot identify a role to link to because roles belong in namespaces, and cluster role bindings along with the cluster roles they reference are not namespaced. Let's apply. And now your cluster looks like this. Even though neither ClusterRole nor the ClusterRole binding defined any namespaces, the dev service account now has access to everything. From these examples, you can observe some behaviors and limitations of RBAC resources. Roles and role bindings must exist in the same namespace. Role bindings can exist in separate namespaces to service accounts. Role bindings can link cluster roles, but they only grant access to the namespace of the role binding. Cluster role bindings link accounts to cluster roles and grant access across all resources. And cluster role bindings cannot reference roles. Perhaps the most interesting implication here is that cluster role can define common permissions expressed in a single namespace when referenced by role binding. This removes the need to have duplicated roles in many namespaces. The typical rules section of a role or cluster role can look like this. However, the above configuration can be rewritten using the following format. It significantly reduces the number of lines and, in my opinion, is much more concise and easier to read. I have other tutorials on my channel about Kubernetes, Kafka, benchmarks, and more. If you're interested, you can watch one of those tutorials.